it might be a good idea to be sure that you have the right definition for the different component. What is a pH, what is a pK, what is a Ka and a Kb. Just to do that, we're going to take the classical generic reaction of an acid plus you're dissolving this acid into water, and this will give you the hydronium ion plus some base. Again, this is acid, this is a base, this is a conjugated acid for water, and this is a conjugated base. So we know that the Ka, which equal to the acid dissociation constant, equal the concentration of H3O plus times the concentration of minus divided by the concentration of AH. The water will be 1. So if you want to simplify, it can be written also by H plus by A divided by HA, knowing that this is this H plus writing, the way you're writing the H plus is a simplification of the hydronium. So for a strong acid, Ka, it's very large, and for a weak acid, the Ka is very small. So the Ka is an acid dissociation constant, and you can take the minus log of Ka, that will equal the pKa. If we take an example of a strong acid like HCl, that will have this relationship here. HCl will give you H plus Cl minus. The Ka value for this relationship is way larger than 1. It's actually around 1 to the 10 to the power of 6. That means very high value here. Okay? So that means that you cannot have that in solution. All of that will be moving toward forming hydronium and Cl minus in solution. If you want to calculate now the relationship between the pH and the pK in this case, you can calculate now what would be the pH of a solution of 1 molar HCl. So again, the pKa is specific for one acid. It is a characterization of the solubility of an acid into a water. The pH is related to the concentration of H plus in solution. That is two different concepts. That will be linked in a few minutes. We'll talk about that. But that's a different, do not mix that. So what is the pH for a solution of 1 molar HCl? That means that if you think about this relationship here, let's take another color here, this relationship here, this 1 molar HCl will completely dissociate it into water and form 1 mole of H plus and 1 mole of chlorine. That means that the pH will be equal to minus the log of 1, it's going to be 1. And this is equal to 0. The pH of any solution of 1 molar of a strong acid, you name it, now sulfuric acid, hydrochloric acid, will give you a pH of 0, which is the lowest pH, one of the lowest pH you can have. But that means that you can have theoretically pH negative pH when you increase this concentration here. If you take 2, 3, 15 molar, for example, of 15 molar with now 15 molar HCl, that will give you 15 mole of H+, so the concentration, the pH, will give you minus log of 15, which equal, in this case, if I'm doing the calculation, minus 1.176. So this is equal to the pH. This is the theoretical pH of a solution of 15 molar of HCl. The problem with that is theoretically you can absolutely have negative pH. If you remember that, the pH is going all the way from 0 to 14. The problem when you're reaching this concentration of acid, the HCl will not completely dissociated inside the water. And again, I want to stress that the pH is not about concentration of H+, it's about activity of the H+. So when you start to add this level of concentration of H+ in solution, of hydronium in solution, the activity will decrease. Part of the HCl will not dissociate as it's supposed to be from a thermodynamics point of view. It will not completely dissociate into the water. That means some of the HCl will stay under the form of HCl and not under the H+ and Cl-. So you're reaching a plateau, and at what point your pH will go, if you want to simplify that, this is not the right value here, with the concentration here, concentration of H+, activity of H+, and this is a pH. You will have 1, 2, 3, 4, and this is going to be -1, -2, -3. You will have your pH that will do this thing here and reach a plateau here, a minimum pH that can be measured. It's very difficult to measure a negative pH because classical electrode, the classical instrument will not be able to measure this negative pH because of acidic bias in the way you're calculating the pH. But you have special electrode, you are able to measure those negative pH. But this will be in disagreement with the theoretical pH that should be here by calculation. Okay, but this is just a small remark to emphasize the fact that you can have negative pH in water. You're not stuck into the 0 and 14. Most of the pH will be in between 0 and 14, but you can theoretically have a negative pH, and you can also theoretically have a pH that is higher than 14 for base, if you have the right concentration. The similar way as the interaction between the H+ in solution start to be a problem at a very high concentration of acid, the interaction between the OH- in solution start to be a problem when you increase the concentration to extreme value for base 2. You understand that the weak acid will not dissociate, and the pKa of a weak acid will be smaller than 1. So if I'm taking another color here again, this is what we're talking about here. The weak acid will have this smaller than 1. If you forget what it means, you go back to your definition here. That means they will not fully dissociate. You will have part of the acid in solution and part of the conjugated base and H+ in solution compared to a strong acid. So I put this table here to show you some example of weak acid here and strong acid here. And you can see that in strong acid you have the famous HCl here and the sulfuric acid in this case. And you see here now you can make the link to the thermodynamics with the delta G. And you can see that those strong acids will completely dissociate, will have a K value that are pretty high because it is spontaneous. It will be spontaneous process. If you're mixing those acid into water, it will completely dissociate. That means those acid here, let's take another color here, those acid here will not be found in solution. You will always only found this part of the process of the equation into solution. The same way as those base here that are very, very strong base will not be found in water. Only this can be found in water. Because as soon as you're touching this base into water, it will dissociate and give you something that is more stable into solution. So the stronger base you can have in water is OH minus, and the stronger acid is the hydronium anion in this case. And the range in pH for natural water you can find in water is set here. That is slightly negative value. Better if I'm using a negative value here. We just discussed this negative value with very high concentration of acid, but you reach in a plateau because of the interaction between the H+. And this is your classical pH. You could theoretically find some extreme value for the pH around 15 here. But again, this is extreme conditions. A few remarks now on acid still. We talk mostly about HCl for acid, which is an acid with one proton only. HCl will lose a proton, right? Giving you H plus plus C minus with a pKa. But some acid have more than one H or proton in the formula. For example, sulfuric acid. With the formula H2SO4. So this will not be written by having that with 2H plus SO4 2 minus. That is the ultimate goal, of course, but that is not how you will write the equation, because this acid will lose the proton in sequence. So this is called polyprotic acid. And if I'm taking this example here, the sulfuric acid will give you HSO4 minus plus 1 proton. This is going to be the first equation with one specific Ka value, with one specific pKa1 value. That is correspond to the Ka1 value equal to the concentration of SO4, concentration of H plus divided by H2SO4. And then you will dissociate the HSO4 minus. That will give you SO4 2 minus plus another proton. That will give you the second equation with a second pK. We call that pKa2, with a Ka2 equal to the concentration of SO4 2 minus, the concentration is getting a bit crowded here, divided by what is going to be the reactant HSO4 minus. So you understand that this will be higher than that because you dissociate the first proton first. This is for sulfuric acid. Now you have other acid with more than one. The phosphoric acid with the formula H3PO4. And of course you understand that you can write it with H2O. You're putting that into water. So let's write it the right way. H2O, that will give you a H2PO4 minus, no, an anion, plus an H plus. Then this PO4 minus plus water will dissociate to form HPO4 minus plus 2 minus plus H plus, and then you will have your HPO4 2 minus plus H2O will give you your phosphate 3 minus plus H plus. And you understand for each of those reactions you will have a specific Ka1, Ka2 and Ka3 with a special pKa1, pKa2 and pKa3. And in terms of value, those will decrease and this will increase. You can write the similar reaction, of course, here for each of those one, but I won't do that right now. But you understand the principle. And another very important system that we will touch in the next following lectures is a carbonate or carbonic acid. Very important acid with the H2CO3 plus water will give you the HCO3 minus, we call that bicarbonate, plus H plus, and the bicarbonate will then dissociate into carbonate and H plus with a Ka1 and a Ka2. Just to give you an example, this is going to be in pure water around 6.5, and this is going to be 10 to the power of minus 10.3. So the pKa1 would equal 6.5 and the pKa2 would equal 10.3. This is an example for the carbonate system. We'll talk about that a bit later. So what is interesting here is those are very key anion in marine system, in most of the system, because they are for phosphate nutrient, carbonate, no, it's a buffer. We'll see that. We'll talk about buffer, a source for calcium carbonate precipitation. If you're having calcium here, the 2 plus, you can actually form calcium carbonate. Sulfate is very important for anything metabolically related in marine environment. We'll see that. So those are conjugated base of an acid. Those are conjugate, I don't know why I'm putting always gated, conjugate base of this acid here, or of this acid here for carbonate. So just to refresh what we talked about that just a few minutes ago, those are base, so they are able to attract H+. And all those elements, especially carbonate, we'll see that, bicarbonate also, and phosphate, you can find that in large amount in marine water, in any water basically. Phosphate a little bit more difficult because phosphate is a very limiting nutrient. Life needs phosphate to build cells, to have enzyme to work. It's very limited and there is not a lot of supply of phosphate in the water, so you will not be able to measure phosphate because the phosphate will be mostly stuck into the biomass. But sulfate and carbonate, plenty of that in water. So why are they not binding to H plus and forming bicarbonate again, or some kind of acid in this case here? For the carbonic acid, because it's a weak acid, you will have an exchange here. The carbonate is not a weaker base than the water. It can compete with the water to get some iron, some H+. So in this case, I should write this relationship as an equilibrium, meaning because this value here is pretty low, you can have an equilibrium between carbonate and bicarbonate. That means in this case, H, a carbonate, can actually take H plus from the water to form bicarbonate. In the case of the sulfate will not be able to grab a H plus from the water to form HSO4 minus. Again, I'm going to explain that a little bit better here. But let's try to illustrate a little bit better this by giving an example here. We have here a bucket, and I'm taking this bucket here, in here, paste, go, and we're putting some water in it. And I'm having in this water some sulfate. Some sulfate in it. The rest, of course, is water, and I have carbonate in it here. So we know that we define that the HSO4 is a strong acid. So when it's dissociating into your HSO4 minus and then the HSO4 2 minus, this relationship here is still a strong acid relationship because this is very fast. Okay, you're moving from one. You will not have this in solution because this is also a strong acid. So even if the pKa here will be very small, pKa1, pKa2, those are very close to each other. That means we will not be able to see this intermediate here. From a macroscopic point of view, the sulfuric acid will right away dissociate and form sulfate. For the carbonic acid, that will form bicarbonate and carbonate. This is a weak acid. So this is a strong one, and this is a weak. And we have saw that the conjugate base of a strong acid is a very weak base. So this here, in this case, is a very weak base. That means that for a weak acid, the conjugate base is not so weak. It's something that will be able to attract proton. Attract proton for what? It's always relative to water. Water can act, as we saw, as an acid and as a base. If you're putting a base that is a weak base, it will, if you want, compete for the proton with water. If the base is weaker than the water will win, and all proton will go to the water. And the water will act as a base. And none of those protons will be attracted by the conjugate base. If you have a weak acid giving you a weak base, but not so weak, part of those protons will be attracted by this not so weak base. As an example for our bucket of water here, if I'm putting HCl, which is a strong acid, you're adding H plus H plus Cl in this case. What will happen to this H plus here? You have water, you have sulfate. We saw that in this case, because it's a strong acid, sulfate will not attract the proton. So the proton will be attracted by the water and form hydronium ion. And in this case, your pH will increase because this is if you want the concentration of H+. If you're increasing that means you're decreasing the pH, changing the pH. I mean your pH will turn more acidic. If you're putting HCl into this bucket of water, you will have H plus Cl minus, and then this Cl, part of the Cl here, will be attracted by the carbonate in this case, because the carbonate is a stronger base than the water. And what we are going to form is some bicarbonate. This is what we call bicarbonate. We'll see the carbonate system in the following lectures, but just to illustrate that. Okay, so you will form this. That means this H plus will not be associated to water. That means it will not increase the hydrogen ion. That means it will not change the pH. This is the notion of buffering. We'll talk about that in the following lecture, but this is something that is worth repeating because it's a concept not always easy to understand. Okay? So, the same way as when you're putting those HCl into the water, it will form H plus that will be attracted to the H2O because the H2O is a stronger base than the chlorine. Chlorine is a very weak base. It will not attract any H plus. You understand that every ion, an ion that you will find in natural water in large quantity, will be weak, very weak conjugate base of any acid around. Sulfate, you can find phosphate, chlorine, because they are not attracting any proton. As soon as you have a weak acid, weak interaction, part of this conjugate base will be able to attract the H plus that you're putting in it. So that's a very important notion to see if the conjugate base you're creating or conjugate acid you're creating will be stronger or weaker than the water itself.